In the last video, I demonstrated how to program the ATTiny85 microcontroller without touching it. I also gathered some experience with shift registers with the intention of building an I2C based output controller. Today I want to combine both aspects by operating multiple 74HC595N shift registers using 3 output pins of an ATTiny85. If you'd like to program along and require more information on how to set up an AtmelStudio project, program a microcontroller, or how shift registers work, check out the videos in the description. Here's the setup. Connected to the PC over USB, we've got the programmer here, the Diamex All AVR. From there, the programmer connects to the Tiny Programmer Mark II switching device, where the ATTiny85 lives. The switch is connected to the board using this 8-wire cable. Everything else on the board is arranged as if the 85 was physically plugged in. 5 volts and ground to pins 8 and 4 don't need further explanation, so let's take a closer look at pins 7, 6 and 5. From top to bottom, they connect to the first shift register's serial input, shift register clock and register clock. Both clock lines are then forwarded to the second chip, so they're both in sync. By using the first register pin 9 output, which is the least significant bit in the setup, as the input of the second register, both devices are daisy-chained together and act as one. This practice can be repeated with as many devices as you like. I'm going to write a little test program next to show the functionality. In a real application, each bit would have some sort of purpose, of course, but this is just a demonstration, so I'm just going to output the value of a 2-byte counter. We're gonna start with a couple of includes, the AVR IO, standard lib, bool, and delay. The delay header requires the F CPU symbol, which should be defined as the current CPU frequency, which in my case is 8 million Hz. I'm also going to have 2 type defs for 1 and 2 byte integers that I use frequently. The 3 output pins that will be used to control the shift registers are pins 0, 1 and 2, or 5, 6 and 7 in the datasheet. I'll use global constants for that, so I know which is which. All 3 pins are combined into a single bit mask. The last constant is timing delay, which is the delay in milliseconds that I'll be waiting between pulling the levels of the output pins high and low. This can actually be 0 and it will work, but I want to be able to play around with the value so I can slow down the clocking in of data if I have to. In order to avoid any mistakes when modifying individual bits in the port B register, I like to have those 2 helper functions available which set or clear the specified bits on port B. The next thing we're gonna have to do is implement the timing of the serial register clock. The device is edge triggered, so when the level goes high, it samples the value at the serial input, high or low, and that will be the next bit to be shifted in. The function to do the job looks something like this. First, we're going to set the level of the serial output depending on the argument. Then we're going to wait a little while so the signal has time to propagate. At this point, the level on the serial clock line is assumed to be low. When enough time has passed, the level on the clock is pulled high, the device clocks in the new bit, and after another delay we can pull the clock line low again. This covers these 3 events in the timing diagram. In order to clock in a whole byte, we're simply going to need another function that loops over every bit and calls the clock in bit function. I'm shifting a least significant bit first, so after 8 cycles the most significant bit will be at position QA. At this point you can probably guess what we're going to do with the multi-byte integers. This setup is limited to shorts, so we're just looping twice, again least significant byte first. When all the data has been clocked in and shifted to its correct position, we need to update the output register so that data becomes visible on the outside. In order to do that, we've got to build a function that implements these 2 events. Just like the serial input, the updating mechanism is edge triggered, so all we have to do is pull the level high, wait a moment, and go low again. Since I don't have any purpose for 16 outputs right now, I'm just going to program a little counter in the main function. As usual, we're gonna have to define our output pins first. Initially, I'm setting port B to 0 here. That means all output pins will be low and all inputs will be floating. The inputs don't matter for now because I'm not using any. The counter variable is initialized with 0 as well. In the main loop, I'm going to send the bits of the counter to the shift register using the clock in short function. When that returns, I call show and the output becomes visible. Another delay for convenience and we're done. Now let's see that in action. I'm going to start with a timing delay of 1 millisecond for safety. That means it will take about 34 milliseconds to clock in the data and update the output register. I want every iteration to be visible for about half a second, so I'll set the delay in the main loop to 500. Let's see. Okay, maybe a little faster. And obviously we've got a binary counter here with the least significant bit on the right. Another thing I can show you in this application is the importance of having a shift register with a separate output stage. Without it, the content would immediately show on the output side, and that would look like this. I set the timing to around 5 and the delay back to half a second again, and it's easy to see that this is not something you'd always want. One last thing that I want to do is measure how long it takes to update both shift registers at maximum speed. In order to do that, I'm going to remove all delay calls and assume it's still gonna work. The counter has 2 bytes, which means all I have to do is stop the time between 0 and 2 to the power of 16, or in other words, the time between all LEDs off and all LEDs on. I'll do this using this sophisticated online tool and my rusty reflexes. Okay, so let's say that's about 9 seconds divided by 2 to the 16th equals something between 100 and 200 microseconds. So that's it for now. As usual, code and schematics are available if needed. Let me know what you think. See you later.